Successive differentiation means taking the derivative of a function more than once. The first derivative f prime of x measures the instantaneous rate of change, like the speed of a car, at a particular instant. The second derivative f double prime of x tells how that speed is changing the acceleration, or how fast the slope itself is turning. Continuing this idea, the nth derivative f superscript n of x is the derivative taken n times. F superscript 0 of x equals f of x by definition. F superscript 1 of x equals f prime of x. F superscript 2 of x equals f double prime of x, etc. Linearity a f plus bg superscript n equals a f superscript n plus bg superscript n for constants a b. If a derivative of order k is 0, all higher derivatives are 0. Polynomial of degree m has 0 m plus 1 cent derivative. The order of differentiation does not matter for smooth functions, mixed partials, commute Clairaut's theorem. A useful analogy is peeling an onion. Each layer you remove reveals a smaller core. After enough layers derivatives of a polynomial, the core disappears, leaving 0. Elementary functions have simple repeatable patterns when differentiated many times. D to the n over dx to the n of x to the m equals case m factorial over m minus n factorial times x to the m minus n when n less than or equal to m, otherwise 0 when n greater than m. Example: d cubed over dx cubed of x to the 5 equals 5 times 4 times 3 times x squared equals 60x squared. D to the n over dx to the n of e to the x equals a to the n e to the x. Thus, each differentiation simply pulls down a factor a. D over dx of ln x equals 1 over x. Higher orders follow the pattern d to the n over dx to the n of ln x equals minus 1 to the n minus 1 times n minus 1 factorial over x to the n. Example: third derivative d cubed over dx cubed of ln x equals 2 factorial times minus 1 squared over x cubed equals 2 over x cubed. D over dx of sin x equals cos x. D over dx of cos x equals minus sin x. After 4 differentiations, you return to the original function. D to the 4 over dx to the 4 of sin x equals sin x. Hence, d to the n over dx to the n of sin x equals sin of x plus n pi over 2. D over dx of arc sin x equals 1 over the square root of 1 minus x squared. Repeated differentiation creates a factorial-like pattern with powers of 1 minus x squared in the denominator. These regularities let us write compact formulas and quickly compute high-order derivatives without doing every step manually. When a function is a composition, y equals f of g of x, each differentiation pulls the chain rule deeper. The first derivative is y prime equals f prime of g of x times g prime of x. For a second derivative, we differentiate again. Y double prime equals f double prime of g of x times g prime of x squared plus f prime of g of x times g double prime of x. The pattern continues. Each new derivative adds terms where higher-order derivatives of f are multiplied by products of derivatives of g. This is sometimes called Fayet-Bruno's formula, but for most engineering problems we apply the chain rule step by step. Implicit differentiation works when the relationship is given by an equation f of x comma y equals 0 rather than an explicit y. Differentiating both sides yields f sub x plus f sub y times y prime equals 0, which gives y prime equals negative f sub x divided by f sub y. Differentiate to obtain y double prime. Differentiate y prime implicitly again, remembering that y itself depends on x. Example: for the circle x squared plus y squared equals r squared, y prime equals negative x divided by y, and y double prime equals negative open parentheses y plus x times y prime close parentheses divided by y squared, which simplifies to negative open parentheses y minus x squared divided by y close parentheses divided by y squared, which equals negative r squared divided by y cubed. Repeating this gives higher-order implicit derivatives. Think of a gearbox. Each gear derivative changes the speed factor and direction sign. Adding more gears, higher-order derivatives compounds the effects, just as the chain rule compounds derivative factors. Leibniz theorem provides a compact way to differentiate a product u of xv of x many times. The statement, the nth derivative with respect to x of uv, equals the sum from k equals 0 to n of binomial n choose k times u superscript k times v superscript n minus k here binomial n choose k equals n factorial over k factorial times n minus k factorial is the binomial coefficient, and u superscript k denotes the kth derivative of u. The proof is by induction. Base case n equals 1 gives the familiar product rule, the derivative of uv equals u prime v plus uv prime. Assume the formula holds for n, differentiate both sides once more. Using the ordinary product rule on each term u superscript kv superscript n minus k produces two new sums, which after reindexing combine to the binomial coefficients for n plus 1. This mirrors the algebraic expansion of a plus b raised to the n. Each differentiation step distributes like the binomial theorem, hence the name. The theorem is powerful because it turns a potentially tedious repeated product differentiation into a single summation involving known lower-order derivatives. Explanation applying Leibniz theorem to specific product forms yields handy shortcuts. Number 1, e to the x times sine bx, the kth derivative of e to the x is a to the k e to the x, the mth derivative of sine bx is b to the m sine of bx plus m pi over 2. Hence, the nth derivative with respect to x of e to the x sine bx equals sum from k equals 0 to n of n choose k times a to the k e to the x times b to the n minus k sine of bx plus n minus k pi over 2. Often this collapses to a combination of e to the x sine bx and e to the x cosine bx with coefficients involving powers of a and b. Number 2, x to the m times natural log x. The kth derivative with respect to x of x to the m is m factorial over m minus k factorial times x to the m minus k. 0 if k greater than m, the jth derivative with respect to x of natural log x is negative 1 to the j minus 1 times j minus 1 factorial over x to the j. Substituting in Leibniz gives a finite sum because the derivative of x to the m vanishes after m steps. Number 3, sine x to the k, where k is a positive integer. Write sine x to the k as sin x multiplied k times. Applying Leibniz repeatedly, or using the multinomial version, leads to a sum over all ways to distribute the total derivative order n among the k factors. The nth derivative with respect to x of sine x to the k equals sum over r sub 1 plus r sub k equals n of n factorial over r sub 1 factorial. R sub k factorial times the product from j equals 1 to k of the r sub j th derivative with respect to x of sine x. Since each r sub j th derivative with respect to x of sine x is sine of x plus r sub j pi over 2, the result is a linear combination of sine and cosine terms. Specific low-order cases, for example k equals 2, give sine squared x equals 1 minus cosine 2 x over 2, whose derivatives are easy. These formulas save time in engineering problems such as signal modulation, where products of exponentials and sines appear frequently. Taylor-Maclaurin series expand a function around x equals 0. F of x equals the sum from n equals 0 to infinity of f superscript n of 0, divided by n factorial times x to the n. Successive differentiation provides the coefficients f superscript n of 0. Leibniz theorem is useful when f is a product because we can obtain f superscript n of 0 without differentiating the whole product each time. Worked example, find the Maclaurin series of g of x equals e to the x times sin x up to x to the 5th. We need g superscript n of 0 for n equals 0 to 5. Using Leibniz, g superscript n of x equals the sum from k equals 0 to n of n choose k times e to the x times the kth derivative of sin x, which equals e to the x times the sum from k equals 0 to n of n choose k times sin of x plus k pi over 2. Evaluate at x equals 0. G superscript n of 0 equals the sum from k equals 0 to n of n choose k times sin of k pi over 2. Compute the first 6 values using the facts that sin 0 equals 0, sin pi over 2 equals 1, sin pi equals 0, and sin 3 pi over 2 equals minus 1. N equals 0, g of 0 equals 0. N equals 1, g prime of 0 equals binomial 1 0 times sin 0 plus binomial 1 1 times sin pi over 2 equals 1. N equals 2, g double prime of 0 equals binomial 2 0 times sin 0 plus binomial 2, 1 times sin pi over 2 plus binomial 2, 2 times sin pi equals 2. N equals 3. G triple prime of 0 equals binomial 3 0 times sin 0 plus binomial 3 1 times sin pi over 2 plus binomial 3 2 times sin pi plus binomial 3 3 times sin 3 pi over 2 equals 3 minus 1 equals 2. N equals 4. G to the fourth of 0 equals binomial 4 1 times sin pi over 2 plus binomial 4 3 times sin 3 pi over 2 equals 4 minus 4 equals 0. N equals 5. G to the fifth of 0 equals binomial 5 1 times sin pi over 2 plus binomial 5 3 times sin 3 pi over 2 plus binomial 5 5 times sin 5 pi over 2 equals 5 minus 10 plus 1 equals negative 4. Thus the series up to x to the fifth is e to the x sin x equals 0 plus 1 over 1 factorial times x plus 2 over 2 factorial times x squared plus 2 over 3 factorial times x cubed plus 0 over 4 factorial times x to the fourth plus negative 4 over 5 factorial times x to the fifth plus dots. Simplifying gives e to the x sin x approximately x plus x squared plus 1/3 x cubed minus 1/30th x to the fifth. This illustrates how successive differentiation via Leibniz directly yields the needed coefficients. 1 f of x equals x to the fifth times e to the 2x. Find the third derivative. Use Leibniz with u equals x to the fifth, v equals e to the 2x. U superscript k equals 5 factorial over open bracket 5 minus k close bracket factorial times x to the open bracket 5 minus k close bracket for k less than or equal to 5. V superscript m equals 2 to the m times e to the 2x. F superscript 3 equals sum from k equals 0 to 3 of binomial 3 choose k times u superscript k times v superscript open bracket 3 minus k close bracket equals binomial 3 choose 0 times x to the 5 times 2 cubed e to the 2x plus binomial 3 choose 1 times 5x to the 4 times 2 squared e to the 2x plus binomial 3 choose 2 times 20x to the 3 times 2 to the 1 e to the 2x plus binomial 3 choose 3 times 60x squared e to the 2x. Simplify, f superscript 3 equals e to the 2x times open bracket 8x to the 5 plus 80x to the 4 plus 60x cubed plus 60x squared close bracket. 2. G of x equals natural logarithm of open bracket 1 plus x squared close bracket. Find the fourth derivative. First, differentiate repeatedly. G prime of x equals 2x over 1 plus x squared. G double prime of x equals open bracket 2 times open bracket 1 plus x squared close bracket minus 4x squared close bracket over open bracket 1 plus x squared close bracket squared equals open bracket 2 minus 2x squared close bracket over open bracket 1 plus x squared close bracket squared. G triple prime of x equals open bracket negative 8x times open bracket 1 plus x squared close bracket squared plus 8x times open bracket 1 plus x squared close bracket times open bracket 1 minus x squared close bracket over open bracket 1 plus x squared close bracket cubed equals negative 8x times open bracket 1 minus x squared close bracket over open bracket 1 plus x squared close bracket cubed. G superscript 4 of x equals open bracket negative 8 times open bracket 1 minus x squared close bracket plus 24x squared close bracket over open bracket 1 plus x squared close bracket to the fourth equals 8 times open bracket 3x squared minus 1 close bracket over open bracket 1 plus x squared close bracket to the fourth. Thus the fourth derivative is g superscript 4 of x equals 8 times open bracket 3 x squared minus 1 close bracket over open bracket 1 plus x squared close bracket to the fourth. 3. H of x equals cosine x cubed. Find the fifth derivative. Write h equals cosine cubed x equals 1/4 times open bracket 3 cosine x plus cosine 3x close bracket using the triple angle identity. Derivatives become easy. The nth derivative of cosine x equals cosine of open bracket x plus n times pi over 2 close bracket, and similarly for cosine 3x with an extra factor 3 to the. Hence h superscript 5 equals 1/4 times open bracket 3 times the fifth derivative of cosine x plus the fifth derivative of cosine 3x close bracket equals 1/4 times open bracket 3 cosine of open bracket x plus 5 times pi over 2 close bracket plus 3 to the 5 cosine of open bracket 3x plus 5 times pi over 2 close bracket equals 1/4 times open bracket 3 sine x plus 243 sine 3x close bracket. Sines follow from periodicity. This compact result illustrates the power of identities combined with successive differentiation. Explanation. Below are 3 past exam-style questions together with a short roadmap for solving them. Question A, JEE Advanced Style. Find the sixth derivative of f of x equals x squared e to the 3x at x equals 0. Solution strategy. Use Leibniz Theorem with u equals x squared, v equals e to the 3x. Only derivatives of u up to order 2 are non-zero, so the sum reduces to k equals 0, 1, 2. Compute u superscript 0 equals x squared, u superscript 1 equals 2x, u superscript 2 equals 2. Then v superscript n equals 3 to the n times e to the 3x. Plug into f superscript 6 of 0 equals sum from k equals 0 to 2 of combination 6. Choose k times u superscript k of 0 times 3 to the 6 minus k. Since u superscript 0 of 0 equals 0 and u superscript 1 of 0 equals 0, only k equals 2 contributes. F superscript 6 of 0 equals combination 6. Choose 2 times 2 times 3 to the 4 equals 15 times 2 times 81 equals 2430. Question B, Gate Engineering. Determine the Maclaurin series up to x to the 4 for g of x equals natural log of open parenthesis 1 plus sine x close parenthesis. Solution strategy. First expand sine x equals x minus x cubed over 6 plus x to the 5 over 120 plus dots. Then 1 plus sine x equals 1 plus x minus x cubed over 6 plus dots. Use the series natural log of 1 plus z equals z minus z squared over 2 plus z cubed over 3 minus dots with z equals sine x. Keep terms up to x to the 4. Natural log of 1 plus sine x is approximately open parenthesis x minus x cubed over 6 close parenthesis minus 1/2 times x squared plus 1/3 times x cubed plus big O of x to the 4. Simplify to obtain natural log of 1 plus sine x approximately equals x minus x squared over 2 plus x cubed over 2 minus x to the 4 over 12. This uses successive differentiation implicitly via known series, but one could also compute derivatives up to 4th order at 0 using Leibniz on natural log of 1 plus sine x. Question C, IIT JEE Mains. Evaluate the 4th derivative with respect to x of open parenthesis x squared plus 1 close parenthesis times cosine x at x equals pi over 2. Solution strategy. Apply Leibniz with u equals x squared plus 1 and v equals cosine x. Compute u superscript 0 equals x squared plus 1, u superscript 1 equals 2x, u superscript 2 equals 2, u superscript 3 and u superscript 4 equals 0. For v superscript n equals cosine of x plus n times pi over 2. The 4th derivative is sum from k equals 0 to 4 of combination 4. Choose k times u superscript k of x times v superscript 4 minus k of x. Only k equals 0, 1, 2 survive. Insert x equals pi over 2. U of pi over 2 equals open parenthesis pi over 2 close parenthesis squared plus 1. U prime of pi over 2 equals pi. U double prime of pi over 2 equals 2. Evaluate the cosine terms. V superscript 4 equals cosine x, v superscript 3 equals sine x, v superscript 2 equals negative cosine x, v superscript 1 equals negative sine x. Compute the sum to get the numeric value. This quick use of the theorem avoids expanding the product fully. These outlines show the typical exam pattern. Recognize a product, limit the number of terms using the fact that high-order derivatives of polynomials vanish, and substitute the specific point after the algebraic simplification. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment.